Hello, welcome to the part 2 of coordinate system. Now we continue with the spherical coordinate system. Okay, in spherical coordinate system, we represent the parameter in r, phi, and theta. Okay, so what is r? R is actually the radius from the origin. Okay, so the r, the radius r, while the phi is actually angle made from x-axis going through here. This is your phi. And the second and the third one is the theta. Theta is actually the angle made from the z-axis, starting and going toward here. So this is your theta. Okay, now we're going to see first what is the range for each of these parameters. So for r, it is from 0 until infinity. And for theta, it is from 0 until pi, which is from here until pi. Pi is in here, is actually in radian. So what is this? Can you guess? So if you want to change it to degree, is actually pi is actually equals to 180 degree. So for the phi is also the same. The the maximum value of phi would be 2 pi. 2 pi here would mean 360 degree. Let's say there we take a point here. Okay, let's say we take a point there. So how we going to label or relate it with the r, phi, and theta? Okay. So here is the point. So you can see for the r value is going towards here is your r value. Okay. So this one is just for easy view, and the next one is in the phi direction. You will have is here. And for the theta direction, so don't confuse, theta direction will be in this direction. So going through here. So let's say if you have 90 degree, the theta will be until here. Okay. For the spherical coordinate system, the differential displacement is a bit special, different than the Cartesian coordinate, which is quite straightforward. So here it is the same dl vector, but we're going to have different ways of expressing it. So expressing it. So here we differentiate first, means we have r unit direction in r, unit direction in theta, and unit direction in phi. So for for unit direction r, there's nothing. It's quite straightforward. It is dr. For phi, for theta, so you can see here, right? For theta, so it's actually here at this region, at this length. We know that we cannot, just like as the case in cylinder, we cannot only use d theta, we can only use angle because the angle is not a length. So we need to multiply with r. So that's why we have r d theta. Sorry, that's why we have r d theta to represent this dimension. Okay, dr is representing this dimension, and you know we have this and we have this. Another one that we miss is this one. Okay, so how we actually have this dimension? Okay, let we take a look first. Okay, so here how we can have this. Okay, let we take out the x y z axis. Okay, so we know that this one is dr and this one is r d theta, but how we can know what is the length, the differential length of this part? So here, okay, we know that dr is the differential of r here, but how we can actually obtain here in relation with this one? Okay, so we erase this first. Okay, how we going to obtain this one? Okay, so first let's say we have this x y z direction, then we have this one, we have our theta, and this one if you take it the same, okay, the same parallel, so you're going to have this theta as well, right? Correct. And you're going to have orthogonal here, you have as a 90-degree angle. So from here, this theta, okay, you have this theta, and you know that this is actually the radius, right? The radius from the origin until at this here, this is the radius. So we want, let's say we want to know this length. So if you know, recall from your trigonometry, sine theta is actually equals to opposite divided by the hypotenuse. So we have sine theta equals to, let's say we want to know this, let's say we put it as b, okay, b over the r, okay, hypotenuse. So we're going to get b equals to sine theta. So sorry, I missed a bit. So we have r here, okay, so this is the r sine theta. So we have this length here over here, it's actually r equals to sine, sorry, so this length is actually equals to r sine theta. Okay, this length here is actually r sine theta, which is, for example, in this case we can make it until here. Okay, this one for this case is actually r sine theta. Now we already have the length in this dimension and in this direction, but we want to have it in consideration with the differential in phi. So for this dimension, we times with d phi. So that's why for this dimension, we have r sine theta d phi, which is this part. Okay. So let me erase all of this. Okay. So now here dr is the changes in the differential of the radius. This one is the changes of this dimension, and this one is the changes of this dimension. Okay, so summarize for the spherical coordinates, the same as the cylindrical and the Cartesian coordinates. So the differential displacement for spherical, we are represented in like this. So, and then it is in 3 unit direction, which is the r, the theta, and the phi unit direction. So what is the magnitude of this is 1, the magnitude of this is 1, and magnitude of this is 1 because it is a unit vector. And this one is the magnitude. So the dr, the r d phi, and the r sine theta d phi. Okay, for example, okay, now we take out again. Okay, so r dr is actually here. Okay, dr in the direction of r. Okay, and r d phi, if we consider this one, the angle, this one is our z. Remember that phi is the angle, sorry, remember that theta is actually the angle made from the z axis, from here. Okay, theta. So this one is the r d theta. This one a bit tricky, but it's not really difficult. It's actually r sine theta d phi. Next is the differential normal surface area. Okay, the same here, dsr, ds normal direction in theta is the normal direction, dsv as the normal direction. Okay, and this is the differential volume, which is r squared sine theta dr d theta d phi. Okay, we continue to the next slide. Next, we're going to see how we're going to evaluate the differential normal surface. Okay, so here we can see this is the normal is in the direction of r. This one the normal direction in theta and normal direction in phi. So you see in here r in this direction. So we can know that the length involved is actually r d theta times r sine theta d phi. Okay, rearrange, you will have r square sine theta d phi sine theta d phi in the r direction. Okay, here in the differential normal surface in the theta direction here, so you know it's dr times r sine theta. So you have r sine theta d phi times dr. Rearranging, you will have r sine theta dr d phi. Remember, it's in the theta direction, so you have theta unit vector. For the ds phi in this direction, the normal surface in the normal one is the phi, so it's actually this r d phi times dr. So r d theta times dr. So we have r dr d theta in the direction of phi.